Hello. Hello. Why is this? Why is the sound not coming from my? Interesting. Okay. Let's just open YouTube video.
Was denkst du kostet mehr, ein Kaffee oder eine Domain bei Strato? Wusstest du schon, wie schnell und günstig Strato für den Kauf deiner eigenen Domain-Website...
So, when I saw fantastic...
Okay. Okay. Whatever. I think I need to change something. I need to download a plugin. I need to add a plugin to streamline my output. Like, because without a proper thing, without proper yeah, whatever. Let's see if OBS is picking up the okay. Okay, whatever. No. Yeah, this is OBS. Okay, yeah, I don't need the functionality anymore to have the live chat. I'm still figuring it out. So, hey everyone. So this is, I'm still figuring out, like, but streaming in Linux is nice. So, yeah. Today we'll be doing some more Lean 4 again, right? So, yeah. And also, I will read the chat like now and then, so don't mind me, right? Pop out chat, maybe something like that. Just send it to 2. Yeah. And a browser source. Yeah. Yeah, okay. Okay. Yeah. So, yeah. Let's do the lean, right? So, I don't remember where we left last time. I'm not going to docs anything for myself, so let's just open lean. So, last time I did like some more customization of my windows to match the I think the theme was, I forgot, something. Let's see. So yeah, we were doing lean 4, right? So let's see. Lean 4. Yeah. So I will go to GitHub. I will go to the lean 4 website. That is, yes, this one. Now what is lean? But I don't want to go to the docs, but I just want to go to lean and get off. Right? Yeah. So this is the website of lean. If you're interested, you could just go there and check some of the things, right? If you're interested in functional programming and other things. So if you go to learn here, in the learn section, there are a lot of things that you can do with lean, right? So here, interactive games and tutorials, right? So today we are going to do something like that. Yeah. So today we are going to do some kind of games, right? Like there is natural number game, there is the lean game server, right? So this is nice, the lean game server, where you can play a lot of different games, right? I like to play this one, the logic game, right? So I finished this the starting already, but I think it's not saved. I don't know how to do that. Oh, okay, I need to download the progress, right? Okay, next time I'll do that, right? But it's fine. I'll do the thing. I'll do the proofs, right? So each tutorial world is accompanied by Redux world with the same subtitle. These worlds are optional. Okay. Okay, there is a Redux world. Okay. Right. So this is nice tutorial. So you can try different type of proofs, right? It is already given nicely what kind of assumptions and what kind of premise is given, right? So I'll highly recommend anyone to play this game. For example, right? I'll start this. So so there is presumptions, right? Like to-do list, like that is type of P, right? Our goal is to prove P, right? So we can just say exact to-do list, right? And that's it. The goal is proved, right? So here exact is what we call tactics. So if you followed up like my previous streams, I used lambdas to do my proofs. That's actually the usual notation to do lambdas to do your proofs, but you can just use tactics also. Tactics are also functional applications, right? It's just a fancy name for lambdas, right? So that's one. I went quite far last time, right? So now we can do for example like an intro, right? So we can do for example exact and intro, right? PS, right? So that's it, right? So what does exact do actually? So what exact does is that it will try to search the goals and it will just apply whatever proposition that you give, right? And later on in this tutorial we'll find out there are other search tactics, right? That are also involved. For example, if you go back, if we start this again, right? So they talk about what does exact tactic actually do. The exact tactic is for now the means through which you give the game your answer, right? It's your way of declaring that you're done. In this level, you are just going to be using one of the assumptions directly, But as you learn how to form expressions, the exact article will accept those two, right? The input will look like exact E, where E is an expression the game will accept for the current goal, right? So that's it. So for example, we can do the same on our Emacs or on our lean instant. Or sorry, I will not use Emacs for this, but I'll rather use, for example, Vim, right? Emacs is quite heavy for this kind of task, maybe, right? We, if you check last streams, we already did some of the things, right? So we can just do that, right? And then logic.lean, right? So yeah, for example, yeah, so I'll remove this. Yeah, so now we need to do example, right? P. We need to prove that we have something, right? To do list of type P, right? That's the functions, and wait, we need to do this like this, the input, right? So we better name this a theorem exact example, right? It takes an input of to-do list of type P, right? And it gives some type P, right? And we need to do, we can just do by, right? And we can say exact to-do list. Type of theorem. Again, interesting. What is it saying? Type of theorem, exact example is not a proposition. Okay. Maybe I just need to do it like this, maybe. P plus P. Right. Have P and H is P exact H. This is so confusing. Example. Right, this works. We'll just do this. Huh. Yeah, whatever. Yeah, I mean, I'm just, yeah, you can just do it later on, right? Using the lean Vim, right? We can just do it later on. So, yeah. So we have exact, right? I haven't still learned how we can do interactively proofs. So far I have been doing the proofs only using lambdas, right? So far, so yeah. So yeah, let's see. Yeah, if anyone is in chat, you can just say hi or something, but it's fine. So that's this, right? Or if you're interested, you can just follow along, right? You can just open this and you can follow along. This is actually very nice, proving theorems, because logic anyone can have, can easily like do this like very nicely. They can just set up the logic part, right? It's nice, if you can, whatever, right? So now what do we have here? Here we are learning about precedence, right? Here we are learning about precedence and a new tactic called have. Currently we just used exact tactic, but here we are doing the new tactic called have. So too many invites. You have invites for Alarfil, Lynn, Oren, Uriel, who all live together. Unfortunately, boxes only have space for 2 items, but you have thought up a clever solution. You will put Alarfil's and Lynn's invites in a box. You will put Oren's and Uriel's invites in another box. You will put both boxes in a final box, nested boxes, right? Nesting boxes like this is a way to get around the 2 items per box rule, ensure that everything is correctly labeled to guarantee each other. Right. So yeah. Okay. So you have AIOU, right? These are the persons, and you represent invited to party or not invited to party as Boolean variables, and you need to prove the goal here, A and I, right? And O and U, right? And you have A, I, O, U with your assumptions, right? The people, right? So the assumptions is that you have propositions A, I, O, U, and you need to prove the goal A and I and O and U, right? So here, what you can do, right? You can just say exact, right? Exact A, I, right? O, like this, right? And one more, one more here. Yeah. So what is this? I just put like AIOU in this thing, right? So this brackets in Lean are kind of constructors, right? It constructs A and I and O and U. Okay, invalid constructor. Okay, interesting. Okay, maybe constructors that doesn't work like this. Let's see. Okay, now first we need A and I, right? So we'll use the have tactic instead of using the constructor and just skipping the B. Yeah. So we just say have AI, right, is equals to and intro, right, AI, right? So now I have A and I, right? Now here it's all about precedence, right? What kind of precedence and how. For example, in mathematics you have BODMAS rule. If the viewers, any of you are into mathematics, in BODMAS you have the precedence. So here in propositional logic, the logical connectives also have a precedence. So you have to think about what kind of precedence this thing has, this propositional logic variable or formulae has. So now if you see here, I have A and I, right? Now I can construct A and I and O, yeah. So or A and I and O and U, right? So those are two different things, right? How can I go about it right now? That's what we need to think about. We'll try both of them, right? So now I'll say have AIO, right, is equals to, I'll say an intro AI and O, right? Let's see what it will give you. So it gave me A and I and O, right? That's fine. Now we'll say again have full, right? Just call it full, right? Now and intro AIO and U, right? Yeah. So it gave me that thing, right? Now let's see. Let's do exact full. Right? It will give me wrong answer because types doesn't match. That means what did we learn about here? The connective precedence. That means this one is not equals to that one, right? So now we need O and U separately. Now that means have, instead of doing this, we'll just say have OU is equals to O and intro O and U, right? Yeah. Now we have both A and I and O and U. Now we will say have full 2 is equals to AI and intro AI and OU, right? So yeah, now we have full 2. See, that's what I'm talking about. See the difference between full and full 2, right? Here, that's the importance of precedence of the connectives, right? So does it go from left to right or right to left, right? In this case, it is from right to left, right? So and or we can just see the precedence table of logical connectives in propositional logic, right? So see, the not operator has the highest precedence, right? That's obvious, and has the higher precedence, and then or, then comes implication, then comes by implication. So this is something that you can remember, this small snippet. And also it comes from right to left. So that means O and U gets binded. After that, the other thing get binded, right? So because its bracket is already given. Now we can say x at full 2. That's it. The goal is done. Level complete. Yeah. Now, now we have and left, right? Here we can say exact and left VM, right? So what it does is essentially use the AND rule, right? One of the AND rules. So that's what happens. We can also say VM dot left, right? That's we've been doing in our proofs. If you see in the lambda proof that I did. So now, instead of and left, we can say exact and h dot right. We can do this also. It also works, right? That's what we did in our lambda proofs in previous streams. If you've been looking into it, now this is interesting. Here we need to use all these three to prove A and U, right? So here we have H1, right? So now we have to have A and we have to have O, right? We can just say have A, that is H1 dot left, right? And have U, that is H2 dot right, right? Now here we can say exact and intro a and u. That's it. Now that's done, right? So exactly what we did here. Yeah. So we can also use this connectives, right, to do this, but yeah. So now we need to prove C, right? So here it's all about how you pick here, for example. So here, for example, if you remember the rules, if we do h dot right, we just only get L. That is useless for us. We need h dot left because that was the previous exercise. So we can do that. Have h1, right? H1 is equals to h dot left, right? That's exactly what we want. Have h2 is equals to h 1 dot left, right? Yeah. Okay. Interesting. Okay. Interesting. Okay. H3. Have H3 is equals to H1 dot right. Yeah. Okay. Now have H3 is equals to H2 dot left. Right? We need H2 dot left. Now we can just say exact H3 dot left dot right. Yeah, that's it. So, or we can just do this directly, right? Or we can do this actually. This is very concise. Yeah. Yeah. Let's see if anyone is in chat. Okay, interesting. I just switch on my thing. Light. Yeah. So this is interesting, right? So we need A, right? Right. We need C, right? We can do this. Exact H dot left dot left dot left dot right, left dot right. Let's see. Have p h dot left dot left dot left dot right. Is it p? Okay. Oh, okay. This is p, right? Yeah, I mean that makes sense. Now have a that is equals to h dot left dot left dot right. Oh, it's s. Oh, interesting. Okay, it's fine. S. We'll just name sp. H dot left dot left HP and S. Okay. Why is H SS H dot left? Let's see. Oh, okay. Why? Oh, okay, right. I mean, it makes sense. I mean, yeah. Whenever brackets gets introduced, the precedent stuff, it gets, yeah. Have a. Now we rename them. SS dot right. Have S. SS dot left dot right. Yeah, now A and S got renamed. Now we need P again, and we get P from P itself, right? Have A or P. We have P already, right? Maybe we don't need to. We have P, A, and S. Now we need C. Yeah. So have C, right? H dot right, dot left dot right dot left. Interesting. Yeah, now we got A. Now we got ACTS, right? We can just use the constructor and exact A, comma C, right? Comma P, comma S. that's it. ACPS. Yeah. So this squiggly brackets is nothing but the type constructor and type constructor. So it's nothing but this and intro, right? This rule and intro rule, right? So yeah. Yeah, that's it. We finished the one word here right now. So yeah, read the word. So yeah, like this we can do a lot of puzzles here. I'm planning to complete this, right? Because here this is similar to logical games where you can construct your own logical games, right? Later on, if you're good at doing lean, for example. We can also do the same. Where is it? Yeah, we can also do the same in lean here, right? We can just do like proofs instead of doing it with lambdas. But the important thing is that you should always understand that you need both. You need to understand both type application using lambdas, right, and also using tactics, because tactics are nothing but something that is lambdas, right? So you can just, for example, you can just do here, for example, check, right, exact, right? So okay, I mean this is let's see, exact. Okay. Okay, maybe we can't do that. How to check tactics? I'm not entirely sure. I mean, it says that it is NAT, type NAT, but how can I check the type constructors of exact? Let's see. Lean for tactics in check. Okay, this is okay. Meta programming lean.elab.tactic. Alright, this is like declaring custom tactics. How can I do this? Yeah, implementing combinators for macro expansion. Okay. Right. Yeah. But as I said, like Lean 4 is good for your mathematical stuff also. I think this is one of the good languages that is being built by Microsoft and the Amazon guys, I think. It's nice. Yeah, let's see. Yeah, they are adding all this meta programming. Recently, I was also looking into meta programming because I got into Lisp, Emacs Lisp. Because I'm using Emacs a lot, right? So in Emacs Lisp, there is also meta programming using custom or using macros, right? Or in Rust, for example. So this is nice that you can also do meta programming. I think functional programming is a type of meta programming. It is already a meta programming in on itself, right? So it's nice that, because if you do this stuff, you will understand how proof automation works usually, because at the end of the day, I mean, what matters for you is proof automation. For you at least. It's nice that they're doing this actually. So they borrowed things from Rust. That's interesting to look at, right? They borrowed things from Rust here. That's interesting to look at, right? Okay. So let's just stick with logic first. So we just use assumption. So assumption is the assumption is a proof search. It just like does a proof search for you using the constructor tactic. So constructor takes already what? Okay. Constructor. Okay, sorry. Now assumption. Right, like, because constructor only finds the and names the assumptions for us, but it does not do it does not finish the proof, right? So we can just do this, for example. This is a nice now okay, we need to do assumption multiple times because we have two goals, right? So interesting. Now if we do constructor, we'll get two goal P and Q, right? Now again we can do constructor and we get P, but we need to do assumption now, and assumption. Now we have R and S, we need to do constructor, right? So constructor basically extracts the proofs or let's go back and see what exactly constructor does. Whenever there's a clear way to create new evidence that matches the goal, the constructor tactic will pick that for you. This replaces the current goal with one or more goals that together complete the construction. For this level, your goal is P and Q. The constructor tactic will replace the goal with two separate sub-goals. Whenever there's a clear way to create new evidence that matches the goal, right? To create new evidence that matches the goal, right? The constructor will pick that for you. So for example, here we have a goal P and Q, right? But we don't have there's a clear way to create new evidence that matches the goal. Okay. The constructor will pick that for you. This replaces the current goal with one or more goals that together complete the construction. Okay, got it. Right. Okay. And to be clear on the definition, for example. Next. We'll go to next. Cases for conjunction. Yeah, we can do cases as well here. For example, cases, right? Our goal is P, right? Cases H, right? And P and Q, left and right. I mean, it splits the for conjunction. It's only for conjunction, and we can just do assumption. Yeah. Right. Yeah. Next. Rinse and repeat. Both P and Q entails just Q as well. Now we can just do cases H, assumption. That's it. Previously we did this with and other things, right? So nothing new, combining your new tactics. So this is important. Assumption, cases, and constructor. You need to do a lot of proof automation or proof tactics here to understand this. This is annoying, this light I have backside of me. I have a light backside of me that's not letting this. This is annoying. Yeah. So nothing new. We need to prove P and S, right? We'll just do cases H1, cases H2. Right. Now we'll just do constructor, and we'll do assumption, and we'll do assumption. Yeah, that's it. Nice. I can navigate the tree. Case SH, cases left, cases right one, cases left, cases left two. Assumption. Nice. Boss level. Oh, this is the same one that we did previously. Case SH. Or we can just do constructor. Or we need to prove A. Cases left. Assumption. Our goal is C, P and S. And we can do constructor again. I need to prove C. Now we can do cases right, and we can do cases right one, and we can do cases left two, and we can do assumption. Again constructor to put P, cases left, cases left one, and assumption. We just have S to prove. We can do cases left and cases left one, and we can just do assumption. Yep. That's this one completed. Let's see this one. So assumption cases constructor exact have, right? What's a birthday party without chips and cake? About conditionals. This world teaches you about conditional statements. In every day sentences, you will see such statements expressed as if, then, logic. When the sky is clear at night, then we will be able to see the stars. This scheme uses the implication arrow. If A, then B. This is the same as A implies B or A implies B. So far, we've been giving our evidence and propositions a real world analogous. Doing this is a bit less desirable with conditionals, as real world evidence is often based on our understanding and not some tangible object. For example, the evidence that if it rained, then the driver generally doesn't come in the form of peer-reviewed physics papers. You should be thinking of the flavor text for each level as an undefined embellishment of the symbols you're actually concerned with. That said, at the level the favor text works on, what would constitute evidence for a conditional statement? Well, for example, if we have gnocchi, butter, parmesan and black pepper, then we can cook gnocchi. And for such a condition, we just be with instructions, right? Okay. So here it's about A implies B. This is simple. So exhibit evidence. So here we can just do it with modus ponens, right? We have P and bakery service. P implies C, right? We can just do exact modus ponens P and bakery service, right? So modus, it's not modus ponens. Okay, it's bakery service and P. Sorry, let's bakery service first. I mean, a lot of people write it in a different way, right? Yeah, so I can just use this modus ponens. Oh, there's a modus ponens tactic also that I didn't know. Interesting. C implies C. You can just do intro, right? C implies C. Exact. Intro C and C. Interesting. CC. Intro. Okay. Intro C and C. Oh, interesting. This is not working. Let's see. Oh, okay. What this is a prop. Goal is C plus C. Let's see what this is. CC is equals to lambda h of type C implies h. Okay. Assumption. Can I do that? I can't do that. Exact CC. Right. Let's open what's up. I need more light. Some okay. Okay, I think today I'm going to end the stream. I think I'm having some hard time to figure out how this thing works. Oh man, maybe it's because of some lighting stuff, or I'm not sure. But when I don't have proper lighting, I can't make this work properly. So I don't have proper lighting. So yeah, okay. Okay, I'm going to end the stream. So thank you for tuning in, whoever that is. So we can see you later, right? Okay, yeah. So I'm a ghost. I'm coming in and out. So see you later. Bye.